Hello and welcome to Still Behind the Bench. My name is Adam, and on this channel I will attempt to describe the science behind distilling spirits in a more technical way. Hopefully it'll whet your appetite to learn more and teach you enough so you're more self-sufficient. For this video I'm going to be talking about Krausen, Barm, fruit caps, pretty much all the other names for this phenomenon of foam, and then I'm also going to be talking about digestive enzymes. So let's get started. Okay, so Krausen, Barm, fruit caps, various other terms, just foam. So what is this exactly? Well, that's exactly what it is. It's just a foam. Now, we know that regular water doesn't foam like this. Tap water doesn't foam like this. Pasta, when you're cooking pasta on the stove, it can start to foam like this. It happens a little differently, but it still happens. And it's because of starches and proteins. So depending on what exactly it is you're fermenting, one of these will be in a higher concentration than the other, or one of them might not even be present. You do a sugar wash, there aren't going to be any starches, but there will be proteins from dead yeast present in there. And that's why Krausen can form with a sugar wash. It's not going to be anywhere near what you get with like a grain wash or a fruit wash or even molasses, but it still does happen. So this is why it happens. You're cooking your mash, and as you're doing that, you're going to be partially denaturing those proteins and those starches. So normally these proteins and these starches are non-polar and they don't like mixing in water. When you go through the gelatinization process for starches, as I showed in one of my previous videos, you're essentially breaking it down so it becomes water soluble, and then you're allowing the enzymes in there to turn those starches into sugars. In this case, these starches were never attacked by the enzymes, and instead what they do is they float to the surface of your wash, right? Same with these proteins, they get denatured. So essentially proteins that are in their normal form, their natural form, are all coiled up in a very complex shape. But when they start to denature, they start to spread out and they can no longer do what they're supposed to do because they can't bind properly to other things. So in this case, they're floating on the surface, partially denatured. So one end of them is non-polar and one end of them is now become polar. So one end of them can now bind with water. It can dissolve in water, and this is called amphiphilic, when one end is non-polar and one end is polar. It's like soaps. Soaps work at getting rid of oils on your dish after eating because the non-polar end can bond to the oil and the polar end can bond to the water, so the water can now wash away the oil. In this case, what happens is you have this surface layer of denatured proteins or partially denatured proteins and partially gelatinized starches. They're floating there on the surface. All of a sudden the CO2 bubble comes up. Now when the CO2 bubble comes up, these starches and proteins will start to form these complex, like interwoven lattices on the surface of the bubble. The polar end of it will stick into the bubble and the non-polar end sticks out into the CO2 because CO2 is a non-polar compound. And this lattice work stabilizes that bubble. So now you have this bubble sitting on the surface, and then another one, and then another one, and then eventually you'll get a layer of bubbles, and then you'll get yeast sticking to them, and then another layer will come up underneath it, and then another one, and then another one, and your Krausen just starts to rise. You get more and more bubbles. After a certain amount of time though, the water that is making up these bubbles will evaporate, and those bubbles will pop. The water parts of the bubble pops, but this matrix, this lattice work of proteins and starches is still there, and they're still forming this foam. So you go from a sort of a closed cell foam to an open cell foam, and now that this foam is open cell, all that CO2 can be released. So after a certain amount of time, as the foam starts rising, the top layer will dry out, it'll release its CO2, and then the layer below that will dry out and it'll release its CO2. And that's essentially what's happening. CO2 is still going to be able to squeak around the edges and stuff. Once you start getting towards the end of the fermentation though, and this entire thing is dried out, now that it's not filled with a gas, it's heavier than the liquid that it's sitting on. So it's no longer going to start floating, it's going to start sinking. And this is when the Krausen or the Barm collapses and sinks down to the bottom of your wash. And that's generally a good characteristic of when the fermentation is finished. You could still let it go for another day or two maybe, but for the most part, when the Krausen or Barm collapses, it's finished. But yeah, it's essentially just these proteins and starches, and it's the same with their pasta boiling on the stove. So where do the digestive enzymes come into play though? Let's talk about that. Okay, so digestive enzymes. As I said in my video on enzymes, they're just special type of protein and they act as catalysts. So they help reactions happen faster. And they do this by lowering the activation energy, which is the amount of energy required for that reaction to happen. So the specific enzymes I bought were these. Enzyme Force by Prairie Naturals. It's made by, Prairie Naturals is owned by a company called Jameson. I think that's who owns them. So I don't know if you can get these exact enzymes somewhere else, or this product somewhere else, but you can most likely find something similar to this. So here's a list of the enzymes it contains. Protein digesting enzymes, protease, which comes from bacteria, papain, that comes from papayas, and bromelain, which comes from pineapples. Contains some fat digesting enzymes, lipolytics, specifically just one called lipase. And in this case, it comes from another yeast, Candida rugosa. I don't know anything about it. Next up, we have our carbohydrates. So it has alpha amylase. We all know that one. Glucoamylase. For those that don't know, glucoamylase also acts on starch. It'll break off individual glucose molecules from the starch. But more importantly, glucoamylase is a debranching enzyme. So with your amylopectin that has all these branches coming off, in order to prevent that branching section from becoming what's called a limit dextrin, which can't be broken down by alpha amylase because it only acts on alpha 1,4 bonds, the glucoamylase can work on alpha 1,6 bonds, which is what creates those branches, and so it can completely prevent limit dextrins from being created. Then we have alpha galactosidase. This is found in beans and peanuts and pretty much all other legumes. It's I don't want to call it a sugar because we can't really digest this. This is the enzyme you find in Beano. Lactase. Lactase is the enzyme that breaks down milk sugar, lactose, which is made up of a glucose molecule and a galactose molecule. Then we got invertase, also known as sucrase, which is just to help break down sucrose, regular table sugar, into glucose and fructose. Then we got phytase, which breaks down phytic acid. So phytic acid itself is not something that we use as a nutrient or the yeast uses as a nutrient, but it can act as what is called a chelating agent. A metal ion chelating agent. And essentially what happens is the phytic acid will dissociate, as most acids do in water. So the hydrogens break off. So the spots where those hydrogen ions were can bond to calcium, iron, or zinc. And now all of a sudden, these metal ions aren't free. In the case of fermenting, yeast can no longer use these. And I know zinc is extremely important for actually making alcohol. It's used in the last step. I'm not so sure about iron and calcium. I'm pretty sure they're also used. I just can't remember where. But the phytic acid molecule has 5 spots where it can, what's called matrix with metal ions. So it can take up, every molecule of phytic acid can take 5 metal ions out. You know, it is found in cereal grains and all the other grains, the pseudo grains, not in as high as the concentration, but it is found there. And anything you can do to prevent phytic acid from chelating these enzymes is a good thing. And I also think that the phytase enzyme might also free up the phosphates found in the phytic acid so that it's free for the yeast to use. So the fiber digesting enzymes. So we have cellulase, which is for breaking down cellulose, and cellulose is just a polymer of glucose enzymes, but it's a very strong one. I don't think this enzyme is actually going to be doing a whole lot. It might do a little bit, but most cellulase and hemicellulase for that matter are bound to things like lignin in the plant, and so they are not easily broken down. You have to break it away from that lignin first, and it's not easy to do. And I don't think these are actually doing a whole lot, but they're there, so they might do something. Pectinase for breaking down pectin, beta glucanase for breaking down beta glucans, which make, in a lot of grain washes, they make your mash really thick and hard to stir. And if it's thick and it's hard to stir, that means it's hard for other enzymes to move around in it. And so you want something like beta glucanase in order to thin it out. And then beta xylanase, I know nothing about, so I don't know if this is doing anything or not. But there it is. This is the most comprehensive set of enzymes I could find in a single product for a not ridiculous price. I want to try and find some other sources that maybe have the proteolytics, at least some of these proteolytics, some of the, I want the fat digesting enzyme, and I'd like the 2 amylases and the phytic acid. That's pretty much all I really need. You know, and the beta glucanase. I also want that in there. You know, pectinase I can add on my own. Technically, I could add these two on my own. Lactase might be nice if I was going to be fermenting something that had milk in it. But yeah, if I can find one that doesn't have as much, but still has these key enzymes, because you know, when you break down these proteins, you're going to be breaking them down into peptides and amino acids, and that's something that the yeast can take in and use, right? Those are sources of nitrogen, so you may not have to add as much nitrogen. When the fats get broken down, you know what, I don't even know what they get broken down into. I should have looked that up before I started this video. And then we know about these already. And you know, if you break down pectin, you won't have methanol being produced. If you break down beta glucans, you'll have a less viscous mash, and pretty much none of the other ones matter. So if I can find one that, so we don't need that, because yeast can make that. Don't need that, right? You can find one that's like that, and it doesn't need all three of these. 2 or even 1 of them would be fine. And technically we don't even need these either, right? But if you're going to be buying a digestive enzyme, it's probably going to have at least one of these 2. So I did an experiment with these digestive enzymes. That's why I bought them. And I was hoping that the enzymes would release more from my chosen feedstock. I chose bananas because a lot of people add sugar when they're making a banana wine. And so I wanted to see if it would release more sugars. And it didn't, unfortunately. But what it did do was it significantly reduced the size of the fruit cap. So I did a side-by-side. I did one with digestive enzymes and I did one with just alpha amylase. The same mass in each of them, 3.2 grams in each of them. And yeah, there was a significant reduction in the size of the fruit cap that formed. And in fact, the one with the digestive enzymes didn't overflow. It didn't fill up the airlock either. And I was actually kind of surprised. So I only did a small scale experiment, but I think I want to try and do this experiment again. So I'm going to talk a bit about the experiment, and then I'll go to the clips I shot of the experiment itself. Hello everyone, here we are back behind the bench. I got these 2 3-liter flasks filled with my banana wash. So each of them has 1.284 kilograms or 2.83 pounds of banana. I blended it up, then added in 1.5 liters of water, 2 tablespoons of citric acid, and then for this one it has 3.2 grams of digestive enzymes, and this one just has 3.2 grams of alpha amylase. So as I said, the main purpose of this was I just wanted to see whether or not digestive enzymes would aid in getting a higher extract efficiency from whatever you are adding it to. In this case, I decided to use bananas because I also want to do a Krausen experiment to see whether or not, if I ferment this one with digestive enzymes, whether or not I'll get that blow off that I've had in the past where a whole lot of foam forms and it just keeps building until it blows the airlock off. So by the time you see this video, that should have happened or not, and I'll talk about it after this part of the video. I made these mixes about 2 hours ago, and every 30 minutes or so I would stir them just so I could mix up the enzymes some more. And while the digestive enzyme one keeps separating like this, by the time I come back it's usually up to about here in separation. This one hasn't separated at all yet. This one is still essentially a banana milkshake. So I'm going to stir them and show you the differences in the viscosity of these mixtures. Let's see if I can get this crappy tripod to stand upright. You can see it does stir, just not very well. See little bits of banana moving there. But yeah, this thing does not want to stir. Just let me wash off my little stir stick here. You know, if we move over to the other one, stir this one up. It's like a night and day difference. Which you'd think it would be, because this has all kinds of enzymes to break down all kinds of things inside this banana wash. I'm just super curious to find out what the original gravity is going to be of these two. See whether or not the thicker one has still a bunch of sugars tied up in the solids that won't make it into my wash. Okay, so I got these 2 flasks fermenting now. Still going, as you can see. So this is the one that has the digestive enzymes in it. And you can see that that fruit cap is pretty thick, but it's not as thick as the other one. So I'm going to take a little quick measurement here. So that's about 6 centimeters, 60 millimeters thick. This is the one with the digestive enzymes. You can see. But if we come over to this other one, the one with just the alpha amylase, it's still fermenting as well, as you can see. And I took the caps off because I was expecting them to explode, but it didn't happen. But we can see the cap on this one is almost double the height. Significantly thicker. You measure it from different parts because it seems to be, it's not symmetrical all the way around. It's double over there. So yeah, so if the digestive enzymes, if they do nothing else, they significantly lower the size of the fruit cap that forms. And all this stuff up here was just me pouring this stuff into the bottle. It's been here the entire time. They were this dirty before. I don't think the cap got much higher than this. This one, on the other hand, though, there's a big chunk of banana here. I'm wondering if it rose that high and has since sunk back down as the fermentation slowed. Can't be sure though. But yeah, this one seems to be clearer as well. And there is less, well, I guess most of the stuff seems to be sitting on the bottom. Well, this one has some on the bottom too. But yeah, fermentation seems much more active here. This is clearer underneath. So if nothing else, you get a lower cap and possibly a much more vigorous fermentation. I'm going to break these two caps down and I'm going to let them go for another 24 hours just to see what happens. All right, that's it for now. So here is where it's sitting right now. Quick little measurement. Almost 1.5, about 1.5 centimeters below the 2,500 milliliter line. And then on this one, we are about, we'll just say 1 centimeter above the 2,000 milliliter line. So in 24 hours, we'll see what it looks like. So yeah, knocked down all the fruit cap and mixed it all up. This one again was, with the digestive enzymes, was much easier to stir. If I look at it, you can see a lot of action going on in there. There's a lot of more space, and the banana solids seem to be a lot more separated. Which makes sense if there's digestive enzymes in there breaking everything down, right? You can see this one looks more solid. Seems like bubbles are a lot more trapped inside it, whereas with the digestive enzymes version, seems like it's a lot easier for them to travel upwards. So that alone could mean that it's, oh, look at that, it's separating before my very eyes. Just means that this could ferment a lot quicker and a lot easier compared to the non-digestive enzyme version. I wonder how true that is for any other ferment, you know, on grain or on mash, I guess you'd call this. Anyways, so that's it for now. Okay, so it's been about 2 hours since that last video where I mixed it all up, and this is what happened. This is the one with just the alpha amylase in it. You know, it essentially exploded. It hasn't come out completely at the top, but yeah, I have to clean that out now. But the one with the digestive enzymes, look, it's still pretty good. Still going, but yeah, the fruit cap is still only about, actually it's collapsed a little bit since before, but it's still fermenting. Now I gotta deal with this. That's it for now. Alright, so it's been cleaned out. I don't even know if I should put this back on. You can see it just sort of bubbling. Here's the Benefit of the 3 pieces is they're easy to clean. 3-piece airlocks. Alright, so I'm going to let this go for another 30 minutes before I come back and check on it. This is my spare bathroom where I do my test ferments. But I have a feeling when I come back, this is going to be filled up. This airlock is going to have banana in it again. I can already see it coming up right there. Okay, so the digestive enzymes version is still fermenting. Slowed down quite a bit though. The Krausen or fruit cap hasn't really changed much. The bottom of it though seems to have dropped out a little bit. But more importantly, the alpha amylase version, I left the airlock off of it last night and you can see that it puked quite a bit. It overflowed and there's a bunch of banana now on the outside down at the bottom. I just put the cap back on top and it's still fermenting. I'm gonna whip them up, both of them up again, probably because there's still probably quite a bit of sugar left in that fruit cap for both of them. And yeah, I want to ferment as much of it as I can in both cases. That's it for now. All right, so here they are now, done, finished. I took samples of them. There is a noticeable difference in taste. This one tastes super sour, probably because I dumped all that citric acid in there. I dumped way more than I probably should have. It was like 2 tablespoons or something. This one, on the other hand, it is also super sour, but it is a different kind of sour. And the difference, I think, is because this one is carbonated slightly because of this fruit cap. Like when I took a sample out of this one, I used my pipettor. Then I was going to use it again as a new tip on this one. But because these are like high school grade flasks, while this one has a perfectly circular and equal opening all the way around it, this one is sort of offset. It's like thicker over here than over here, and this hole isn't uniform and it wouldn't fit. So I used the tube method. And when I stuck that tube down through the cap, there was a whole bunch of off-gassing, carbon dioxide being released. So this cap is acting sort of like an actual seal and helped carbonate the liquid a little better. And I think it's that carbonation in this one that's sort of mellowing it out a bit. So it's not as sharply sour as this one. Pretty fascinating change. I'm still surprised at how thick this cap is and how much hasn't dropped off compared to this one. Those digestive enzymes do a huge amount. And this one is clarifying so much quicker too than this. Let's see if we can... I gotta clean these things off. It's gonna be a pain. So yeah, when it comes to fruit caps or Krausen, if you're worried about it overflowing, it seems that these digestive enzymes, if nothing else, they will take care of that. This one overflowed. Like at first it flowed up and into the airlock, and then I let it go without the airlock. Like I took the airlock out and it overflowed right out, and as you can see down the side, there's a whole bunch in the bathtub as well. All right, let's go back to the bench and discuss this some more. Okay, so the video portion that would normally be here, the file was corrupted for some reason. So I'm replacing it with a frame from the last clip and doing a voiceover on the computer. So I did take an original gravity before I started fermentation. You may have seen it in one of the clips. It was 1.050, so 50 gravity points. That said, it isn't exactly an accurate value. The true value is closer to 1.040 because the citric acid threw off the original gravity value by 10 gravity points. I calculated out how much the citric acid would alter the specific gravity, and because I added way more citric acid than I should have, 2 tablespoons in 1.5 liters, it altered the specific gravity because that is way too much citric acid. When I took a final gravity reading after the fermentation, it read 1.010, again off by 10 gravity points because the citric acid isn't consumed during fermentation. The true final gravity would have been 1.000. So with the citric acid, what you put in stays there until the end. So my potential ABV would be around 40 gravity points, which is approximately 5.3%. Could have actually been higher or a bit lower. Certainly smelled and tasted between 5 to 6%. But I put in the citric acid without originally planning to. It just hit me that these enzymes normally sit in your stomach for a while, and so they probably work best under acidic conditions. So I rushed to put the citric acid in, and I measured it volumetrically with tablespoon measures instead of using a scale like I probably should have. So it wasn't very exacting, but it is what it is. I don't think it made a huge difference in terms of fermentation though. Next time I do it, I'll only add a small amount of acid before I pitch the yeast, but I'll also take the original gravity before I add the acid. As you saw in the video, I also taste tested them both. The one with just the alpha amylase enzymes was actually slightly carbonated, and that seemed to have mellowed out the acidity from the citric acid in terms of flavor, but that actually wouldn't matter after distilling. The issue though is that during distillation, it could cause a puking issue. So after removing the solids of the mash, it would be good to whip it up to remove any CO2 should a similar situation exist with a larger batch that could actually be run in a still. So let's go back to the bench now. All right, so before I get to the end of the video, I'd just like to thank my Patreons. I can't thank them enough for the support they give to this channel. If any of you would like to help support this channel, there is links in the description for Patreon, a one-time PayPal donation, and there's also a merch store. No pressure though. Back to the digestive enzymes. So we saw they knocked down the fruit cap, and the same thing's going to happen to any Krausen or Barm that you have. We also saw that it thinned out that really thick mash in the beginning. And that's going to happen with pretty much any mash you use. Like rye and wheat have a lot of both beta glucans and proteins, and that can make the mash really thick or viscous, and it's a pain to deal with. So what you could do is you mash at a really high temperature to do the gelatinization and liquefaction. Then what you do is you bring the temperature down, throw in some digestive enzymes, wait like an hour, 30 minutes to an hour, and then you can let it cool a little bit more and pitch your yeast. Unless you're going to be lautering. If you're not going to ferment on the grain, then you'll want to remove everything before you pitch your yeast. That's it for this video on Krausen's and digestive enzymes. I hope you learned something. Please click like and subscribe to learn more, and have a great week.